So this is a video for day I'm missing for a topic on combining radicals. And so in lieu of me not being able to be here, I'm going to make this video. Just a bit of a review for what happened last week before Thanksgiving. Before Thanksgiving weekend, we did a topic. Mr. Bonnet gave that, and it was on just finding factors. And then on the Thursday before Thanksgiving, I gave a lesson just talking about how to simplify radicals. So today we're going to do combining radicals. And the plan today is that kids who are taking Dash 1, this lesson, all of it applies to you. Kids who are taking Dash 2, there's going to be a slide somewhere through here. I pointed out before where there's two roads that end up getting dividing a fork in the road. And at this point here, kids who want to do Dash 2, that's kind of your stopping point. The amount of outcomes that we have, the difficulty level for Dash 2 on radicals is not the same as Dash 1. And so basically what I'm going to ask is that Mr. Bonnet's going to take kids who want to do Dash 2, and you guys have the rest of the period after this to do some work on your assignments and whatnot. And the kids who are going to stick around with Dash 1, just keep watching the video with the sub for the day. So anyways, here's our lesson. We're going to talk about combining radicals. As I talk about this, I want to reference first a couple of other things. For example, the term like. The word like in math is obviously different than the word like in everyday life. It's not like I like a person, right? Like in math means like similar. Maybe it's a better concept to work with there, like similar radicals, right? When we talk about like terms, 3x and 4x, those are things that you could add together to get 7x, right? But are 3x and 4y considered like terms? Well, no, they're not. So you have no ability to combine them. And if you come across that sort of scenario, you would just have to leave it the way it was. You can't actually combine things. Today, what I want to work on is how to combine radicals in many different ways. We're going to start by talking about how to combine like terms. Eventually, we're going to do things where we multiply and divide as well. So let's start with this first slide here. So if you have a root 5 and 4 root 5s, the answer is 5 root 5s. It's because you have 1 of something. This is the something. And then you have 4 more of the same something. 1 plus 4 means you have 5, but of the same something. I mean, really, the root 5 could be replaced by a smiley face. 1 smiley face plus 4 smiley faces is 5 smiley faces, right? Only rather than smiley face, these are all root 5s. Okay. So here's an example of something that do not have the same radicand. They are not like radicals, so you can't combine them. Last note I have on the page here. And this applies really to math in general going forward, regardless of Dash 1 or Dash 2. Whenever you're working with a square-rooted number, a radical, just leave it there. There is no value in converting root 6 into 2.54, etc. Especially for those of you who are in my physics class, you'll recognize that rounding becomes a huge, huge issue. And it's just better to leave it as root 6. That's an exact value. It's exact. There's no rounding to it. There's no question of, well, should I make it 2.5? Should I make it 2.45? Should I make it 2.452 or whatever the next number is, right? This is a perfect form. So don't try to put it in your calculator and square root it. Okay, so let's try some more examples here. These ones all involve the operations of either adding or subtracting. We're going to start with those. And the goal here is that these things do not currently look like they have like radicals. Like this is a root 50, this is a root 2. Based on that, let me show you some things that are incorrect. You would not say that it's like, say, 1 root 50 plus 3 root 2. You wouldn't say that it's 4 root 52. That would not be right. You don't take 1 and 3 and add it together and 50 and 2 and add it together. Because that's not how you would have added 1x and 3x. 1x and 3x would be 4x, but these things had to be the same. And the 50 and the 2 is not. So we're going to use the skill that we've been practicing since before Thanksgiving. We're going to break down the root 50 into smaller values. Mr. Bonnet showed us a concept about how looking for all the prime factors works. What I'm going to recommend is we're going to start looking for things that are perfect squares. And so I would have done this starting on the last lesson I did there. Although 50 can break up into a lot of things, like say 5 and 10. And that's not wrong. I say this lots in math. It's not wrong to break it up into 5 and 10, but it's not helpful. I think the most helpful object would be to go 2 and 25. The reason being that 25 can actually square root to the number 5. And then the 2 will have to stay behind under the square root sign, right? So this is what we did last week, Thursday. At this point here, do we have like terms? Yeah, you have 5 root 2's, you have 3 root 2's, so you have 8 root 2's. New color for a new spot. So similar concept here. We're going to try to find a way to break down. I'm going to use that as like a, I don't know, is that a verb? Yeah, action word. We're going to break down larger radicals into smaller ones, and then if they're like radicals, then we'll put them together. So I think the 5 is stuck though, right? The 5 is not going to work, but we can do 27. 27 breaks up into a lot of different things. Well, okay, actually not a lot. 1 and 27, but maybe the best one is 3 and 9. Why did I choose 3 and 9? Because 9 square roots. It square roots to 3. So the 3 comes on the outside, but the remaining 3 stays behind. Same logic with the 80. I need to find a perfect square number that goes into 80. And there are lots of numbers that go into 80, like say 1 and 80, 2 and 40, 4 and 20. 4 is good, right? Because 4 actually is a number that's a perfect square. But there's a better one than just 4. I believe 80 divides by 16 to get 5. So this is the best solution. And Mr. Bonnet said this the first day for the lesson. Maybe you didn't catch it. It stuck out to me because I kind of knew where we were going to go. But he said that you need to have good ability to work with your divisibility rules, knowing what 80 can actually divide by. And knowing that 80 divides by 16 is really helpful then, because 16 can actually square root to give a 4, and the root 5 stays behind. So 12 is 1 and 12, but that's not helpful. 2 and 6, not helpful. 4 and 3 is, though, because the 4 can actually square root, right? So if 4 square roots to 2, that 2 has to come on the outside here, and it multiplies by whatever number is already out there. So the 2 times the 2 means you have a minus 4 outside, and the root 3 left over. Okay, well then based on that, we just need to combine like terms. These ones here are like terms. Minus 3 and minus 4 gives minus 7 root 3's. These ones go together. 3 minus 4 would be minus 1 root 5. These ones cannot get combined. It's not possible. They're not like terms. So do not do this. So I'll put 2 lines here. Do not try to make it like minus 8 root negative 2 or something like that. I mean, first of all, you can't even have a negative root, right? But you don't go 7 minus 1 is 8. Well, you do that, right? You do the 7 minus 1 if they're like terms. Do not change the thing under the radical. That's not how it works. So back here is our actual answer. Yeah, another thing we've been working on is now adding in variables. It doesn't sound like, from what I've talked to you about, that you've done much or if any of them last year in grade 10 with Mr. Kwan, which is fine. But I do need you guys to be proficient in working with them now. So if we throw in some letters, does it change things? Well, 4 root x, really, there's nothing you can do with it. It's 4 root x. But this 9 right here on this one here, you can break 9 up into a couple of 3's. I mean, we could break it up into 3's or just recognize, doesn't 9 actually square root? Square root's 2, 3. So that 3 then will times by the 4, it multiplies to give 12, and then you have root x. So the 9 square roots to 3, the 3 times by the 4 for 12. Now you have like radicans. 4 and 12 is 16 root x's. For this last example, right off the bat, it does not appear that they actually have square roots in the same sort of way. This one's obviously got a root, but this one's got a fraction. But I've thrown this one in here to remind you, and this is still something that should be reviewed from last year. So this is -1 or -2. Whenever you have the bottom of a fraction as an exponent, that actually implies the type of root there is. In a previous set of notes, I would have told you that like x to the 1/2 is the square root of x, or x to the 1/3 is the cubed root of x. Whatever the bottom number is, that's the kind of root there is. Now, the way this works, though, is that only x is to the power of 3 over 2. So the 3 is out front. This 2 right here means that it's a square root. And what's it a square root of? Well, x to the 3rd. So what you really have here is a 3 of a root x to the 3rd and a 2 of a root x to the 3rd. And although they had looked nothing similar at first, they actually mean the same thing. I'll make sure that's clearly a 3 there. It's a 3 now. So 2 of something and 3 of something is 5, root x to the third. We're not done, though. We want things in simplest form, and this is not considered simple yet because this x to the 3 can be simplified a little bit better. Reminding you, x to the 3 really means x times x times x. Or maybe another way of putting it is x squared times x. There's still 3 x's there. But 2 of them can get square rooted, right? And if you square root the 2 of them, you can actually kind of pull an x out front and make it 5x, right? And so now the 2 of them have kind of come out in front, and the one remaining one stays behind. And that's kind of the new twist that hopefully you've been working on over the last little bit. I would have shown you that on Thursday. Just the idea that we can work with variables in the same way. So, okay, hopefully that first slide made sense. Now would be a good time to pause, and if you have questions, maybe ask a friend or buddy or Mr. Bonnet or our sub. We could replay that if you need to, but if not, then we'll move on and try some more challenging examples. So, the next thing I need to do is show you, well, what happens if we multiply? And the first thing I need to point out is that this is not foiling. This is not like 2 times 4 there. This is not a binomial. The only reason why it kind of looks like that is I put it in brackets just so that you can kind of keep them separate. But this is meant to be 2 root 7 times 4 root 75. That's what it's intended to be. So here's how the rules for this work. If I gave you 2x times by 3x, what you would have done there is you'd have done 2 times 3 is 6, and x times x is x squared. Right? The same kind of rules apply here. You're going to take your numbers, as opposed to those not numbers, right? But your numbers like 2 and 4 and times them together to give 8. And you're going to take your radicand numbers and multiply them together. So you do 7 times 75, which is 525. Now, I'm just going to do a quick check. Does 525 actually square root on its own, or do we have to break it down? 525 does not square root. Okay, so the advice I'd give here maybe is rather than making it 525, that is an option. What you could just do is make it 8 and then like 7 times 75. Because I think this is more useful in this format here. The 7 and the 75 do times together to get 525, but let's just re-break them up into some factors. Because I can see how 75 might work nicely. 75 is actually 3 and 25. Why was that useful? Kind of a rhetorical question. Hopefully you answered in your head, but it's the 25, right? This 25 can actually square root to give you another 5. Where does that 5 go? Well, it goes on the outside of the square root sign along with the 8 that's already there. The numbers that we didn't use then were the 7 and the 3. Last step, combine them together. 8 times 5 is 40, and 7 and 3 is 21. Our final answer to this is 40 root 21. Let's try the next example. Sometimes just examples is good, right? So what we're really doing here is taking minus 3 root 2x, and we're multiplying it by 4 root 6. So take your outside numbers, your coefficients, that's a better word to use, your coefficients, and multiply them. So minus 3 times 4 is minus 12. Then take your radicands and times them by each other. Right? Just like here, your 2 times by your 3 for your 6, and your x times by your x for your x squared. The 2 and 6 will have to give you a 12x right there. Okay, now it's nowhere near as large as it was for the 525. Right? Because the 525, I just broke it back up into numbers that I could find a perfect square out of. This one's pretty easy, I think. 12 is really a 3 and a 4. Why did I choose 3 and 4, not 2 and 6 or 1 and 12? It's all based on this 4 right here. 4 can actually square root. And the more you do this, you kind of speed this process up, right? 4 square roots to 2. The 2 comes on the outside and times it multiplies by the 12. So 2 times the 12 is minus 24. So we've used the 4 up, turning it into the 2 that came out there. The remaining stuff is this 3 right here and the x. So there's the skills for how to multiply. Now we're going to combine that with some of our algebra skills. Now I know I promised Dash 2 kids that algebra was done, and it is in the sense that we're not solving for x. I still need you to know how to do things like foiling, expanding, but we're not actually going to solve for anything here. But you still need to know how to do, like, say, the firsts the outsides, the insides, and the lasts, or however that works. So we can still FOIL something like this as well. And this is -1 or -2 still. So, well, let's walk through it. We need to FOIL those terms together. 8 times 9 is 72, and there's a root 10, because that's 2 times 5. I'll color code this to help make it organized. I'll times these ones together. -5 and 6 gives you -30. This guy doesn't have a root. In a way, I guess it does. It's 5 root 1, I guess, because isn't root 1 just 1? 5 times 1, really? So, long story short is that there's a root 10 sitting there as well, which is super convenient, because maybe you can predict where we're going to go in a future step, because these guys are like terms. I'd recommend maybe putting them together later, though. I don't want to make a mistake by jumping the gun here. So we need to do this one. 8 times 6 is a positive 48, and the 2 times the 10 is a 20.
Please excuse the instructions. Dylan Baxter, can you please come to the office? Dylan Baxter, please come to the office.
And for the last one, you can see that the 9 and the 5 will times together to give a -45. And then there's really only the root 5 left on the 9, because again, this guy doesn't really have a root. So let's start putting like terms together. Hopefully you'd agree, I'll use purple for this one here, that these two contain like terms, don't they? They're both root 10s, right? So 72 minus 30 means you'd have 42 root 10s. Over here, these guys, they don't have a like radicand. But the 20 can get broken down into 1 and 20, not useful. 2 and 10, not useful, but very useful is the 4 and the 5. Not so much for the 5 just yet, but for the 4. Because 4 square roots to give 2. So I can kind of remove that, turn it into a 2. 48 times 2 is 96, root 5. Hey, this is convenient. The -45 is also a root 5. 96 minus 45 means you'd have, hope I didn't screw my math, 51 root 5s. This would be your final answer. 42 root 10s and 51 root 5s. Some kids might then say, hey, hang on a sec, Chris. 10 and 5, can't I put those together? Can't I make a 10 like a 5 and a 2? And then like I pull the 2 out? So there's like a 5 here and a 5 there. But that's not valid because we're looking for numbers that are perfect squareds. If we had 2 2s, which was 2 squared, or 4, totally we can square root that. But that's not what we had. We just had 1 2. And so although, yes, 10 and 5 do have like a common factor, not as roots, they don't. So unfortunately, we do have to leave it at this format here. Okay, we are almost to the point where we're going to split up here. That fork in the road is coming very soon. So here's kind of like the last of the challenging questions. It looks kind of intimidating. Don't get me wrong, it's going to look scary at first, but we have to simplify things one at a time. I would say the most intimidating things for kids when they see this one then is, whoa, like big star exclamation mark, what the heck, a 3 over 2. But remember, this is from grade 10 curriculum. If you have like an x to the 1/2, it means it's the square root of x. If you have an x to the 3 over 2, it means it's the square root of x to the 3rd. So I'm going to deal with just this little piece right here. This means you have 2x. All of that's to the power of 3. That's being square rooted. That's what that means. The over 2 means it's square rooted. The bracket means that both of these things now are to the power of 3. Which means that, yes, x is to the power of 3, but the 2 to the 3 actually means you have 8x to the 3rd. So, long story short, everything I've just highlighted in red is actually an 8x to the 3rd. It's been disguised in a different format, but that's what it should look like. So now I'm going to write it a bit differently again. I'll use a new color. What we're doing is we're taking a -2 root 11x, and it's almost like we're distributing it across 2 terms. One of the terms is a 4 root 8x to the 3. You can see how this 4, I kind of carried it down here. I didn't write it in front, but it was always sitting in front of these guys. And 4 root 8x to the 3. And then we have a minus 3 root 3. Maybe FOIL isn't the right word to use here. We're just distributing, right? We're expanding. We're going to take this outside term and times by that term. This is all a term. And then because of the minus sign in between here, then here's the second of our terms. So let's give it a try. Outside numbers. Minus 2 times 4 is minus 8. Square root. 11 times 8 is, yeah, I'll times them together. Why not? It's 88. And then x times x to the 3 is actually x to the 4, because you add the exponents. Then for the other term, minus 2 multiplies by minus 3 for positive 6. And then for our square roots, the 11 times is by the 3 for the 33 with an x. Well, they don't look like they're going to combine, but we should simplify them at the very least. So 88. I could have left it as 11 by 8, but I thought 88 was worthwhile because I'm going to look for a number that's a perfect square that goes into 88, and I think I know one. It's 4 and 22. The 4 square roots to 2, and minus 8 times 2 is minus 16. The 22's got to stick behind. And since 22 doesn't divide by like 4 or 9 or anything, it's kind of stuck there. X to the 4 means you have 4 x's, right? Or you have a couple of x squareds. So each of those can kind of get square rooted on its own. Long story of that short being that you have 2 x's and x squared that can come outside. So that is how you simplify this term. That's probably one of the more challenging things you need to be able to handle, is dealing with both variables and numbers underneath the square root sign. Right here, though, for this next guy here, the 33, I mean, the only thing it breaks into is 3 and 11. They're both prime, so nothing is going to happen there. So it's just going to have to stay where it was. And these things are not like terms for so many reasons. For one, the 22 and the 33 are different. This one has an x under a square root sign. This one doesn't. This one has x's outside the square root sign. This one doesn't. So this would be our final answer. Okay, good news. If you're wanting dash 2, that's the extent of what I need you to be able to do. The long and short of it is, if I give you a square root of a number, I need you to be able to take it to that. If I throw some letters inside, I need you to be able to handle that as well. I also need you to be able to add these things together and possibly do some foiling of them. But that's about it. That's where we're finishing. So this is our last slide before the fork in the road. A radical is considered to be simple if it does not contain any more factors that can be removed. If you leave something as, like, say 4x root 8x, you're not done, because 8 has another 4 that you could work with. So you should keep going and take that 4 out and put a 2 out here and make it 8x root 2x. So if there's a number still inside that can be removed, not even just a number, even if like there's the variable has enough of them to get removed, you have to do that. However, this next step here is actually not something we'll cover with you guys in dash 2. So I will with kids who stick around, but at this point here, here's our fork in the road. So our dash 1s are going one way and our dash 2s are going a different way. And this is going to be for a foreseeable future. So I mentioned this last week sometime. What's going to end up happening is when we finish this unit up here, I'm going to work with dash 2 kids on statistics, and Mr. Bonnet's going to work with dash 1 kids on patterns, and then we'll do some flipping. We will merge together briefly at some point, and we're totally coming back together at the very end. These roads will merge and come back together for trigonometry, because there's some similar trig outcomes. But for the next while, we're kind of going in 2 directions. So, dash 2 kids, Mr. Bonnet will take you then. Go work on your assignments. They are due by the end of the unit. Finish them whenever you can. I'd recommend earlier than later, because when the answer key is sitting up on the clipboard at the front, you can go mark it yourself. So, give some wait time while you guys do that. Dash 1 kids, we've got to continue. So, I'm sitting in a classroom by myself making this lesson. I have no idea how long I need to wait for you guys to do this. So maybe press pause if you need more time for transitioning. But I'm going to keep going now. So here is where dash 1 kids next need to go. This is also part of what's considered simplifying. Simplifying says that the radical is not part of a denominator of a fraction. I need you guys to also handle dividing with fractions. And the long story short is that if you ever have a square root on the bottom of a fraction, that's not considered simplified. There's some reasons for this. Part of it's just a standard convention. We like to write things with square roots on the top rather than on the bottom of a fraction. Ancient like Babylonians and Egyptians and Greeks, they were able to, and I don't even know how, but they were capable of doing these calculations. They were able to do root 3 divided by 3. That's something they could handle. They knew how to estimate those values. But for whatever reason, they were not able to do 3 divided by root 3. If the root was on the bottom, they had an issue with it. If the root was on the top, they had a way of solving it. And because of that, standard convention has become, this is not considered good enough. We have to convert it to a different format. Now, you don't actually just flip the fraction upside down, by the way. That's not what you do. But that was just an example. But hopefully you'd agree with me that then this is a problem based on what we consider to be standard convention. You can't have a root 3 on the bottom. So here's how we solve it. We solve it similar to other fractions. We are going to multiply by a fraction that's really like 1 over 1. Only it's not going to be 1 over 1 we're going to use. And maybe for the first couple, I'll just show you what we'll use, and then you'll figure out how we got that. I'm going to times by root 3 over root 3. Hopefully you'd agree, root 3 over root 3 is just like timesing by 1. It's kind of like common denominators, but here's the trick. On the top, 5 will times by root 3 to give 5 root 3. On the bottom, you'll have a 2. I'm not even going to write it yet because we're not ready for it. But wouldn't you agree that root 3 times root 3 is root 9? Isn't root 9 just going to go right back to being 3? Right? If I had to prove this, root 3 times root 3, isn't that root 9? Because 3 times 3 is 9, right? Isn't root 9 just going to give you 3? Or another way of looking at it, don't you have a root 3 squared? Right? You have 2 of them, right? Well, doesn't these cancel each other? And that's the whole point as to why I chose root 3 over root 3, because the 3 here will cancel, and this little bit right here will just be the number 3. So if root 3 times root 3 is 3, it still has to times by 2, though, to give us 6. And this is now considered simplified. So rather than writing it in this format with a square root on the bottom, we found a way to convert it so the square root's on the top. And, I mean, I know it's almost arbitrary, but historically, that's what was considered simplest. Square roots on the top are considered to be okay. Square roots on the bottom are not considered to be okay. And that's just based on how ancient Egyptians or Babylonians first were learning math as they were kind of figuring it out thousands of years ago. Nowadays, we don't really care because we got a calculator and computers that can handle putting square roots on the bottom. But they didn't have those back then. They had like, I don't know, those little abacus things with the little beads you slide across a... Anyways, let's try another example. Right here, we have a square root on the bottom. And we don't want the square root on the bottom, so we're going to multiply by a fraction. And the fraction is always going to be some sort of square root over a square root. And our goal is to try to find what square root that should be. Last time, it was 3. Well, it's the same thing this time. We're going to make it root x plus 2 over root x plus 2. Whatever this guy here is, we're just going to multiply by itself. The reason being, on the top you'll have minus 4 and a root x plus 2. On the bottom, the root x plus 2 will times by the other root x plus 2 to literally give x plus 2. Now, I put it in a bracket, though, because really this 2 that's sitting out here should really multiply across both of them. But I'm not going to distribute that this time, because hopefully you'll see something else that's useful. So the best answer, rather than foiling the 2 back in, is to actually call it minus 2 root x plus 2's. And you're dividing by x plus 2. Again, it's kind of arbitrary that we chose for the square root to be on the top. Because essentially all we've done is we've taken the square root from the bottom and found a way to slide it on the top. It doesn't just work that simply where you just, hey, look, now there's a root up here and just, cancel. You do have to do all these steps, but that's considered simplified. You can have a root on the top, not on the bottom. It may even be necessary to multiply what's called a conjugate. This is a word we'll use for more challenging scenarios. And you can kind of see why the dash 1 and dash 2 have diverged on these paths here, because this next step got a lot more complicated all of a sudden. So this is why this is more of a -1 scale. If we were to times by root 6 over root 6 right here, this is not correct, by the way, so maybe don't write this down unless you really want to do the wrong way of doing it. Or maybe it's not mathematically helpful. Maybe I should change that. This won't be wrong math, it just won't be helpful. Watch what happens when I try doing this. 2 will just stay there, and root 3 times root 6 will become root 18. Then what's going to happen here is when I times the root 6 by the root 6, it'll just become the number 6. That's awesome. But this root 6 has to kind of times by both of these values. So it would have to times by the 4, and then it would give you 4 root 6. Did we actually get rid of the square root off the bottom? The answer is no. And mathematically, this is still equivalent. It's still the same, but it wasn't helpful. So hence the little blurb I have at the top here. We need to multiply what's called the conjugate. And again, sometimes it's just easier to show you the trick a couple times. And eventually you'll pick up on why it works. So this is going to be what we multiply by. We're going to multiply by a binomial. Kind of like multiplying by like an x minus 2. That's what we're going to multiply by. You might ask why, Chris, why would this work? But follow with me. On the top, you're going to take this and times by that and by that. So 2 times 4 will give you 8. And the root 3 that times is by the 4 will just be a root 3. There's a root on the top, not a problem, we can live with that. Then we got a 2 times essentially like a minus 1. And then the 3 times by the 6, 4, and 18. Can I have square roots on the top? Sure, no problem, go for it. What we're hoping for, though, is on the bottom that we'll also have no square roots now. And this is more of a traditional FOIL. I'm going to go 4 times 4 for 16. I'm going to go root 6 times minus root 6. Root 6 times root 6 is just 6, but it'll be minus 6. Here's where this is brilliant. Whoever came up with this conjugate idea had a great idea. When you times these ones together, the 4 times the root 6, I'm putting this in a new color specifically for a reason, by the way. It's going to give you 4 root 6. And when you times this 4 by that negative root 6, it'll give you minus 4 root 6. Yes, you were supposed to get square roots, which is normally a bad thing. We don't want them. But the brilliant thing is that they'll actually cancel each other. This is a difference of squares. This is like x minus 2 and x plus 2. When you FOIL it out, you get x squared minus 4, because there were some middle terms in the middle, but those middle terms, they kind of cancel each other. So it's brilliant, actually. I will do more examples, and you guys can rewind this if you need, by the way. Don't feel like you can't rewind, because here's your final answer. There's a 10 on the bottom now, because 16 will just minus 6, and we no longer have square roots on the top. Do these guys have like radicants? Well, no, they don't, but we're not actually done. This is a common mistake kids will make. They'll miss that the 18 can still be reduced because 18 is 9 times 2. And I'm going to start speeding up a little bit here. 9 becomes 3. 3 times this by 2 for minus 6. Hopefully I didn't do that too fast there, because hopefully you're getting a little bit faster at reducing. 18 is 9 and 2. 9 square roots to 3. 3 times this by 2 for 6, and 2 stays behind. It's getting faster, right? But this is now considered to be simplified. There's no longer a square root on the bottom, and I can't combine the 3 and the 2, and they're as simple as possible. So, okay, I've got a couple examples left here. I think in the interest of time, maybe what I'll do is I'll do one of them, and then I'm going to have you guys try the other one and see what you can manage. So maybe I will leave this one. I'll leave this one. You guys see if you can try that one yourself. I'm going to do this one over here, because this one probably is a little more scary. It looks scary, but it shouldn't be. A 1/2 just means there's a square root there. That's all. Don't stress. So I guess I'll just rewrite it. Okay, we have a binomial on the bottom. The way we get rid of a binomial is we times by a conjugate. So I'm going to have 3x root 3x thing, but I'm now going to add root x. See how this is a minus right here? I'm going to create a binomial situation here where I add my roots. And if I do this properly, the bottom, I guarantee you, will no longer have roots when I'm done. But I have to do a lot of foiling. So I have to do a really good job of keeping track. If I times this by this, you're going to have a root 3x to the 4. If I do this times this, I'm going to have a root 2x. That one there will give me a root 6x to the 3. And that one there will give me an x squared. All of them on the top still have square roots. Watch the bottom though, this is brilliant. Root 3x to the third, when I times it by another root 3x to the third, will just give me 3x to the third. Really? Because the square root signs will cancel. And when I do this one together here, the root x and the root x, I mean technically what's happening is a root x is timesing by a root x to give a root x squared, but that just gives x. So you can just minus an x. If you were to FOIL the other terms, I guarantee you they're going to cancel, because this one here is going to give you a negative something, and this one right here is going to give you a positive something. I'm going to erase all my lines there because all these lines are getting a bit much. But this one and this one and this one and this one, I guarantee you a difference of squares, they'll cancel. So on the bottom, it's just a 3x to the 3 minus x. It's fantastic. On the top, I have a little bit of work to do. Here, x to the 4 can turn into an x squared. This guy right here, I can't actually simplify at all. Here, there's actually 3 x's. 2 of them can come out front, but the 6 and the x have to remain. And here, this is kind of like what we did on the bottom there, a root x squared times by itself, square rooted kind of thing. Well, it's now just x. None of them are like terms, but at least they're all simplified now. So we are done, by the way. We almost could have factored out an x. I want to show you something. See on the bottom here, you could have factored out it and made it x, 3x squared minus 1. On the top, this guy has an x out front, this guy has an x out front, and this guy is an x. It was almost possible for you to factor out an x and cancel some stuff. However, the only reason why that would not have worked is that this term right here did not have an x outside of the square root sign. I know it has one under the square root sign, but it doesn't have one outside of the square root sign. So anyways, erasing all this stuff. This then is our final answer. And this is kind of what separates dash 1 and dash 2. Our answers are going to often look very, that's gross, right? Like that's not a fun sort of thing to finish with. Okay, last example. What we are going to do then on Thursday, once I'm back from my scope, we're going to be able to solve a question like this. We need to throw the equal sign in. And we're going to put like everything together. I'm going to have fractions divided by each other. I'm going to put 1/2 exponents in there, and we're gonna solve. Right? I'll show you that method in a little while. If you want to take a stab at it, you can. Don't feel like you have to. So anyways, going forward from here, we have one last lesson. The solving radicals one is just for you guys in 20-1. Okay. In the meantime, you have a work day, I think, tomorrow. The goal would be, and this is for really everyone, make sure that you finish the first assignment in a very timely manner. Don't leave it for forever. I'm not putting a due date on it, but you should finish it as soon as you can so you can get some feedback. I'll have an answer key ready for you. Mark it yourself. As soon as you finish the first one, start on the second one. And truth be told, if you get stuck on the first one, maybe print off the second one and start on the second one anyways, because you might be able to do some of the questions on the second one. And, like the first question on the second assignment, you might be able to do before the 5th question on the first assignment. So anyways, the 2 assignments are due at the end of the unit. You guys are marking them yourselves like normal. Don't lose them, obviously. Don't cheat. Don't lie about it, because I will look these over at some point. So, okay, anyways, I'll stop the lesson here. Hopefully that made sense. If not, it's on YouTube. You can watch it again or rewind it or watch it as a class. If you have questions, let me know for Thursday. We'll talk again on Thursday when we do this topic. So, okay, have a good day, guys.